So we start today on page 34. First, we'll have a look at the calendar. Today is, what, 25th. So we do parametric equations, although we started these last time. So we will finish the official, class number 33 at some point during this class, and then we'll start on the next class's worth of stuff, which will mean we have plenty of time to review for our test. We'll have all of, what is the 30th? Is that Monday? We'll have all of Monday plus part of Friday to review for Wednesday's test, okay? So our last test of the year, not counting the final, is a week from today. Also, project number 8 is due at this moment, so hopefully project 8 is in the folders. I've already gotten it from some people. And then we have a quiz on Friday. Okay, and the quiz on Friday.
I thought it was Monday. I came prepared for it today.
No, sorry. Yeah, so the quiz is on Friday. Any questions on calendar stuff? Okay, and not to get ahead of ourselves too much, but the end of the semester is rapidly approaching. Our exam, let's see, the last day of the classes is the 14th, so we are here on Wednesday. So we have like the rest of this week. Next week is a full week. Then we have a full week, let's see, so next week is the full week in May, another full week in May, and then the 14th is Monday. So we have 2 full weeks plus the rest of this week plus Monday. So it's less than 3 weeks. It's the end of the semester. That 14th is the last day of all classes. If you have a Tuesday, Thursday class, then actually the 10th is the last day that you will meet your Tuesday, Thursday classes. And then the rest of that middle week in May is final exams starting on the 15th. Our exam is the last day of the exam week, and it's on the 18th. Questions on any of that? Okay, so I know that we're tired, and I know some of us are sick, and I know we are crawling towards that finish line. I'm right there with you, but we've got to muster and push all the way through. Okay, so that is that. Next thing I want to look at is something that Tacite had found. Tacite, can you explain?
Which I think is neat because it makes me then like if we were to Z over 2 and we're finding all 2, it's still in the same shape. And in fact, like no matter what n is and no matter what the number is, we still get a really.
Okay, so let's so we're going to move Z around a bunch, but let's first think about x to the 6th equals 1. Can you hold up the number of fingers that is one of the answers to that question? There's a very nice value of x. X equals 1 works. There is another, quote, nice value, another real number that when you take it to the 6th power, it's equal to 1. What is that? It's -1, right? So you can see the 2 answers. One of them is here on the far left at -1. The other one is there right on Z. Z is the x. It's the original. Sorry, Z is the 1 on the right-hand side. And there's 2 nice numbers there. But how many solutions does that equation have? We know it has 6, and so we want to find the others. And so we did this whole process, and it turned out that we ended up with a bunch of different angles that we should go to, and one of the angles would send us up to this guy, and that angle, I guess, was 60 degrees or pi over 3. And I don't know if we thought about the, like the symmetry here, or I guess the picture, but the next angle being 2 pi over 3 is like just like shifting over rotating by the same 60 degrees every time. And so you just kind of keep rotating by 60 degrees to land on all of your things, and you get that nice little like hexagon, like this little pattern there. And so those are all 6 roots of the number 1. Now what's going to happen if I take this guy and make it bigger? I'm going to move Z straight to the right to 2. I want to know all the 6th roots of 2. Well, is there a real number that is the 6th root of 2? No? Can you not type the 6th root of 2 on your calculator? One point. Okay, so there's a 6th root of 2, right? 1.12-ish. Is what is the negative of that? Another answer? Yeah, because taking it to the 6th power gives you the same positive 2. So it's gotten a little bit bigger, right? So maybe that green dot on the far left will move a little bit to the left. It'll go to like negative 1.2. And this green one at the far right, which you can't really see, will move to the right a little bit. What about the other dots? They're going to go out the same rate. Yeah, I mean, remember we had the same, remember the RE to the I theta, that business, RE to the I theta. And what did we find? Well, we found 6 different angles, but what about the R? Did we find like 6 different R's? We found a single R. We had one single R, and maybe you could have a plus or minus. So you could end up picking a couple of different values, but we just picked one R and we stuck with it. And then we just found the different angles. And again, maybe we didn't think so much about the picture, but this will show us that everybody is going to move radially outward exactly the same. I'm moving this to 2. I moved Z quite a bit. I moved that way out to 2. Did the other guys move a lot? No. In fact, they moved 0.12 away. That's what you guys found. If I move out to Z equals 3, what's going to happen? Cube root of 3. Can you find the cube root of 3? Sorry, the 6th root of 3 on the calculator? Okay, so this dot is going to move to 1.2. It's currently at 1.12-ish, so it's going to move a little bit to the right, not even as much as it went before. So you can see like dramatic changes in the right-hand side of the equation. Don't have a whole heck of a lot, don't correspond to much change over there. And then we can kind of play the same game. What if instead of 6th roots of, let's bring this back to 1, instead of 6th roots of 1, if I wanted the 5th roots of 1, how many dots would we see? We're going to see 5 of them. Can you hold up the number of fingers that is a single 5th root of 1? 1. So one of the dots will stay right there where Z is. And we're expecting 4 others. That's like a hexagon. It's called a regular hexagon because all the sides are the same and all the angles are the same. What kind of a shape am I going to get if I want the 5th roots of 1? A regular pentagon. And so you can maybe predict even what the angle is going to be. There they are. And what if I wanted the 4th roots of 1? Get a regular square, regular quadrilateral, or just a square. And maybe that's not so surprising because can you name all the numbers that satisfy x to the 4th equals 1? So we had 1, we had negative 1. What are the 2 imaginary numbers that satisfy that? It was I, right? What is I to the 4th? I squared was negative 1. This was like our fundamental definition for I. So how much is I to the 4th? 1. So I satisfies that equation. Where is I in this picture? It's right up at the top. There's I. Now what's the other number that satisfies? There's negative I down at the bottom. And so you can kind of peel these guys apart and find all the different nice symmetrically shaped things. Those are the 3 cube roots of 1. Wonderful. I guess we can go one more. The 2 square roots of 1. It's part of a nice collection of like polygonal type shapes. And there's no reason to stop at 6. You could have a 7 or an 8 or 9. I mean, it goes further, but this application stops at 9, tacitly. Mm-hmm. That's it. Do you guys remember when we did that plus 2 pi k at the end? And if we had 9 roots, then we would end up with a 9 theta equals. And so you'd end up taking 2 pi and dividing by 9. And that's exactly how much you want to rotate around by every time. Very good. Plus the colors get added. That's not, I didn't know that. Okay, so that's fine. And then we did one more thing. You guys actually didn't just find the 6th roots of 1. You found the 6th roots of some complex number. What was it? It was like -5 minus 3i or Was it that? I wonder, like all the wonderful stuff I could have in my brain, but instead I'm storing -5 minus 3i from last week. I think I have an anniversary coming up. Okay, so I can't quite get to -5 minus 3i in this picture, but I think that all 6 of the answers were imaginary numbers for the ones that we had. We're still expecting 6 things. We're still expecting this kind of symmetry because there's going to be a single r, which means they are equally spaced around the origin. And we're going to get the same 2 pi over 6. We're still going to be rotating by the same angle every time. But I think instead of being tied to the number 1 here, we find that maybe they're tied to something else. So it's still on a circle, still a real nice hexagon there, but none of those is a real number. All 6 of them are imaginaries.
Is there any way to angle it so that you can have a 6th root of a complex number?
6th root of a complex number that ends up with a real number?
Yeah.
So I feel like when I'm getting it to kind of rotate around, but it felt like, it's a good question, but it feels like we need to land back on the reals to get, yeah, and not just the reals, we need to land on the positive reals. If we zip over here, yeah, that's kind of cool. Okay, Tacite, thank you for finding this. Very nice. Okay, so let's come back to page 34. And on page 34, we were playing around with these things called parametric equations. And so, for example, here is a set of parametric equations. X equals t plus 1 and y equals 2t. And so the first thing we were doing to try to get a sense of what that graph looked like before we type it into the calculator was just to make our table. So let's go ahead and make a table here just to kind of refresh our memories. What values of t should we pick? 0 through 5. All right, so let's actually just go 0, 2, 4, and 5 something. We'll just skip a couple of them just to save some time. Any questions on, don't copy those numbers from the board. Plug in, and then look up and agree with the numbers that are on the board. Any questions on how to plug into parametric equations? Just one little time saver. I find it faster to do all the x's and then separately all the y's because I can, instead of going column wise, I go across because I can do t plus 1 pretty easy. Oh, okay, just add 1 to all the t's. And then separate rule. Oh, just double all the t's. So I think it's a little faster to do it that way. Once you've got your points, go ahead and plot. In this case, we have 4 points. So plot 4 points over there in the diagram. Okay. Indeed. Thank you. So it looks like the points are maybe lying on a line. It's hard to know because being the evil math teacher I am, I didn't let the grid go far enough. I'll have to fix that. But then how do we actually know whether or not it's a line or a curve? What's the thing we do to translate those two equations into one that's more familiar? Get rid of the t. You guys remember, eliminate the perimeter. So we can solve this guy for t. So we get t is x minus 1. We solve one equation for t, plug it into the other, and hopefully you get something that's familiar. And y equals 2x minus 2 is familiar. What is it the equation of? A line. What's the slope of that line? 2. And it is. You can look at the picture. What's the y-intercept of the line? -2. Okay, this one doesn't have a y-intercept because it stopped right there. And in fact, I probably shouldn't have put an arrow at the top. I probably just should have stopped it because this one has a definite start and a definite end because of this part, 0 to 5. And but if it had continued, it sure feels like maybe it would have hit -2 as the y-intercept. Fair enough. What's the difference between part A and part B? Yes, the range of t values is different. Instead of going 0 to 5, we're going to go -5 to 5. So what do you think is going to happen to that picture over there? We're just going to continue. We're going to get more to the left of this guy. So if you wanted to find maybe the new starting point, what value of t should I plug in? Let's plug in -5 for both of those t's. What do I get when I plug -5 in? -4, -10. -4, -10 is down there. And definitely that's going to be the start of the graph. So it just gives us more of the line. Questions on that? Okay, so when we're ready, we'll go to the next page. We're going to graph some parametric stuff with trig functions in it. So now x is cosine of t, and y is sine of t. And before we do anything, I want to try to get some intuition about this. First of all, cosine of t, cosine of anything is always trapped between what numbers? 1 and -1, right? Definitely. So that x is always between 1 and -1. So what I'm going to do is I'm going to go ahead and trap it. I'm going to put some dotted line here at 1, another dotted line there at -1. I know the graph is somewhere in between there because x never gets to leave that space. How about the y values? Same thing. So what kind of lines can I draw now if y is always trapped between 1 and -1? Horizontal. So this graph is now very tightly trapped in between all those lines. It is something inside of that little square. It can never leave that square. And before we plot points, before we make a table, again, just trying to get some intuition about this. X is cosine of t, and cosine of t bounces between 1 and -1, right? Sometimes it's 1, sometimes it's -1, and it just goes back and forth, back and forth. So in my mind, I'm kind of imagining that the x part is just going back and forth, back and forth. It's doing something like that. But it doesn't just go left, right, because there's the y equal the sine of t. So the sine of t is also going to bounce, but it's going to bounce between 0 and 1. So yeah, so like I'm just trying to get a sense of what it's going to do. You know, like is it going to be like, you know, like kind of gradually like shading in, and then maybe we'll shade back down, you know, like that's a possibility. Like they're both kind of working together, and we want to try to get a sense of what it's doing. So let's plot some points. T, X, and Y. What's the first T we should plug in? All right, so it says 0 to 2 pi, so we're obligated, 0 to 2 pi. Let's go ahead and do 0. Let's do pi over 4. Let's do pi over 2. And then one more, we can do pi. You guys try those 4. So you can use your calculator here. I mean, the unit circle is fine, but we're going to be plotting points, and it's easier to plot decimals than to plot radical 2 over 2. Probably nearest tenth is okay. No, because we're going to be plotting these points, so decimals are easier for us. So once you've got your points, go ahead and plot them on the graph.